Really cool new discovery by the James Webb Space Telescope detected the chemical signatures for the first life in an extrasolar planet outside of our solar system. This is just an artist's representation here, not a real image, but it's mind-blowing that we actually may have detected the first signature for life outside of the Earth. Now, this exoplanet is orbiting a star, a red dwarf star, which is cooler than our sun in the constellation Leo. And it orbits about every 33 days in what's called the Goldilocks zone, which means it's not too hot, not too cold, so that liquid water could potentially exist on this planet. Now, this star system is about 124 light years away. Remember, the closest star is only about 4 light years away, so this is still relatively close. If you can find the Big Dipper and then trace down, you'll find Leo where this star system is located. Now, through spectroscopic measurements, what the James Webb Telescope actually discovered was a signature in the atmosphere for something called dimethyl sulfide and dimethyl disulfide. Now, these are compounds that are usually produced on Earth by marine phytoplankton. And what they do is the organisms create this compound, goes into the atmosphere, and then it bonds with other things and it disappears from the atmosphere over time. So the only way that it's really replenished, at least on Earth here, is through microbial life constantly producing it and pumping it into the atmosphere. Now, you might say, how can they actually detect these things from so far away? What they really do is look at the light of the star passing through the atmosphere of this planet. So as you know, the light of a star is really a rainbow, all different wavelengths. Well, what you have is you can have molecules absorb certain wavelengths, preferentially depending on how the electrons are in the orbitals of the molecule. And when the electrons decay back down, they re-radiate light at those wavelengths, but in all directions. So if the starlight is coming through and some of it is being absorbed and re-radiated in all directions, then from Earth, we actually see a deficiency or lack of energy at certain wavelengths. And you can see these dark lines in the spectrum here. And that corresponds specifically to different molecules. So they saw the fingerprint in the spectrum from these two chemicals that are indicative of life. Really exciting finding. Everything you've ever touched in your life is made of one of these roughly 100 elements on the periodic table. As we go across the table from left to right, the protons in the nucleus increase by 1, and the electrons surrounding also increase by 1, so every element is neutral. On the left-hand side of the table, we have very reactive metals like sodium and lithium. Metals like to lose electrons in reactions. On the right-hand side, we have the non-metals like oxygen and chlorine. Non-metals like to gain electrons in reactions. In the middle of the table, we have the common metals like nickel and copper, and they also like to lose electrons in reactions. When a metal, like sodium on the left, comes in contact with chlorine on the right, it sends its electron over to the chlorine, and they become what we call ionically bonded. That's called table salt. So what is a photon anyway? In truth, no one really knows the answer, but we do know that photons of light have characteristics of being a wave, but also being a particle, and that's part of the weirdness of quantum mechanics. In wave theory, if we see two waves lining up where the crest of the waves are lined up together, then when you add them together, you get a larger wave on the output. And in a similar way, if the crest of one wave lines up with the trough of another wave, when you add them together, you get a destructive output where it adds to 0. But we learned also that light has a particle character. When a photon hits an electron, it can only eject the electron from the atom if the energy of the wave is high enough, and we figured out that the energy of photons come in discrete chunks. Now, this is a little picture of what you might visualize a photon to be, something that has a wave-like character, but also is sort of localized in space. Now, we're all taught as kids that the nucleus of every atom has protons, which are positive, and neutrons, which have no charge at all. And we're also taught that like charges repel. So the protons in the nucleus should be strongly repelling each other and trying to blow the nucleus apart. So why does the nucleus stay together? Now, the answer to that question is something that we don't learn in elementary school, and that is that there's a force stronger than the electric attractive and repulsive forces, and that's called the strong nuclear force. The strong nuclear force doesn't really reach outside the nucleus at all, but it is millions of times stronger than electric attraction and repulsive forces. So that's why every atom in your body stays together, because even though the protons are trying to blow the nucleus apart, the strong nuclear force is millions of times stronger, holding it together. It's honestly hard for me to even conceive of what the Earth must have been like during the last ice age. You can see that the ice sheet extended all the way down past the Great Lakes to about the 45th parallel when the last ice age was here about 10 to 20,000 years ago. This was a layer of ice somewhere between 3 to 4 kilometers thick. Glaciers actually flow. How do they flow? Well, obviously, they're sliding on rocks and ground underneath and gouging the earth underneath. That's how the Great Lakes were formed. But actually, they also flow because the enormous pressure from the ice actually melts a very thin layer of the ice at the boundary interface. If you think about it, when water freezes, it does expand. So compressing it with pressure from the glacier kind of reverses that and makes a thin sheet of slushy water under the glacier. So when you use the word equilibrium, there's kind of like the everyday definition, and then there's the definition in physics. The everyday definition of equilibrium, it kind of means like the steady state. What will the system, whatever system you're talking about, do if you let it reach some natural settling point, okay? The equilibrium of a seesaw, if it's exactly balanced, might be to be horizontally across. But if one child is sitting on one side, the equilibrium might be slanted to the ground. The equilibrium of some sugar that I'm stirring in a glass of water, if I agitate it for a long time and let the system reach equilibrium, there'll be some concentration of dissolved sugar in there. There's even equilibrium in an electric circuit when you charge a capacitor. What final charge will it reach, for instance? All right, now in physics, when we say equilibrium, what we're saying is that the forces are really balanced on an object. Entropy in physics is the measure of the disorder of a system. One of the laws of physics is that entropy of a system must always increase, and so over time we expect systems to get more and more disordered. However, we can see very complex structures in all of life, and so it seems like life is getting more and more structured and goes against one of the laws of physics. Life is not violating entropy. The law is better stated that the entropy of the universe must always be increasing. Even though your body has a high complexity and low entropy, all of the energy that you get from eating food, breaking down all of everything into nutrients, is leading to an overall increase of entropy of the entire universe. Here's a balloon popping at 1400 frames per second. And here it is at about 3600 frames per second. As we go along here, we'll slow it down more and more. Here it is at almost 6000 frames per second. Take a look at how the balloon splits apart and then flies into the background. Notice that at the point that the needle hits the rubber, it splits at that point incredibly fast and then blows apart, almost splitting the balloon in half from that point. Here we are at about 10,000 frames per second, and you can see some dust inside of the balloon. It looks like the inside of this balloon is coated with some sort of powder. And here it is at about 20,000 frames per second. Well, it's Friday, and that's when we play everybody's favorite game, Will It Freeze? So we get the liquid nitrogen in the cup, and we're going to freeze a banana. Okay, so we have our freshly peeled banana, and in it goes. It's making quite a cloud here. We'll let this sit for a few minutes and see how cold we can get it. Now, liquid nitrogen is at negative 195 degrees below 0 Celsius. So negative 195 below 0. So it's boiling away, and so we have to keep adding it. We're going to keep doing this until it stops boiling and it'll be totally frozen. It's starting to simmer down a little bit and stop boiling quite so much. We'll top it off. Okay, so here we're going to go ahead and take it out. 1, 2, 3. Extreme close-up. Happy Friday, everybody. Here we have a ping pong ball suspended in a column of air from a hairdryer. If we're careful about it, we can actually get 2 ping pong balls to be suspended in the same column. The high-speed air flowing around the ball creates a low-pressure region, and then the outside air pressure forces the ball to stay in the column. We can actually tilt the column of air to about 10 degrees before the ball falls out. This is called the Bernoulli principle, where high-speed air or fluid causes a low-pressure area. If we constrict the airflow further by placing a tube around the column of air, we can force the ball to be shot upward. It's been known for a long time that magnets can exert a force over long distances. These forces can affect other magnets and other certain metals which can be magnetized. We've also known for a long time that magnets can influence a compass needle. Magnets can do this because they are surrounded by an invisible field called a magnetic field which can influence nearby objects. One of the greatest discoveries in all of science was learning that electric currents produce their own magnetic fields. Here we can see the magnetic field surrounding a wire with electric current. It turns out that electricity and magnetism are linked together. If we run an electric current through a coil of wire, we can concentrate the magnetic field and attract nearby metals. The higher the current, the stronger the magnetic force. Two like poles of a magnet repel each other, while the opposite poles of two different magnets attract each other. With powerful magnets, these attractive and repulsive forces can be quite strong. Surrounding every magnet exists what we call a magnetic field. This magnetic field always exists in closed loops around the magnet, coming out of the North Pole and extending and entering into the South Pole. As the magnetic field extends throughout space, it exerts a magnetic force on certain materials that are able to be magnetized. It then attracts those materials. The magnetic field is ultimately a quantum mechanical effect that comes about from the alignment of electrons and their spin axis in a magnetic material. An electric circuit is a closed loop that causes electricity or allows electricity to flow. There has to be a closed loop. The closed loop, the electrons come out of this black wire, come into the other camera frame, through the light bulb, into this wire, which is looped a little bit. Then it goes through the switch here, and then back around and now back into the frame of the power supply right here. Voltage is the push. The reference point for this voltage on this readout is between these two terminals. So it's telling me there's 2.25 volts, but it's the units of push that exist between these two wires. The display right under this, the electric current resulting from that push. So the unit of voltage is volts, and the unit of current is amps or amperes. As I increase the voltage, the current is going up. As more current flows in the circuit, the bulb gets brighter. If I put a resistor in the circuit, the current goes down and the bulb is dimmer. It's frequently said that when the electricity is turned on in a circuit, it's the speed of light. It travels at the speed of light through the wire. What we call the drift velocity of the electrons in a circuit is only about a millimeter per second. So if you track a single electron and you say, okay, I start from here and then 1 minute later I see where it is and it's over here, it might only have gone 1 or a millimeter or a tenth of a millimeter in a second. That is not anywhere close to the speed of light. So why do we say electricity goes near the speed of light? Here's why. Because the individual electrons are colliding and going crazy. So if you track one electron, it's not moving very fast. But as soon as this electron goes here, the next one immediately gets pushed the other way, and the other one gets pushed the other way. So there's sort of a chain reaction effect here. When one electron gets here, it kicks the next one out, immediately vacates its shell. Or if you want to think of the other way, once this one gets sucked out over here, there's a vacancy that's immediately pulling this one over, and then another vacancy that's immediately pulling it over. There's a chain reaction, so it's like as soon as one comes out, whoom, there's like a chain reaction where everything tries to move. But when we say electricity travels close to the speed of light, what we're saying is when we turn the voltage on, the current is flowing almost instantaneously, almost near the speed of light, because the chain reaction of when this one comes out to this one moving over here, that is almost at the speed of light. If you remember from math class, there are 4 types of conic sections. Guess what they are? Parabola is a conic section, ellipse is a conic section, circle is a conic section, hyperbola is a conic section. So the orbits of anything in space have to basically be one of these 4 shapes, and they're all conic sections. The reason we care about that is because when Newton formulated his law of gravity, and he came up with this form of the law of gravity, The way he was able to derive it is because they had astronomical observations of the positions of the planets. So they knew that the orbits of the planets were elliptical, and they knew the precise position of them, and so they basically had Newton figured out what would the form of gravitational force have to be in order to produce the motion in that elliptical shape. And it came out to be an inverse square law like this. Newton was a smart guy, probably one of the smartest people that ever lived. This is a superconductor. If you cool it down with liquid nitrogen below its critical temperature, it loses all electrical resistance. This means that it repels all magnetic fields, and when we drop a magnet, it tries to repel the magnet off. However, if we drop the magnet a little higher so that it sort of gets forced down into the superconductor, since there are impurities in the superconductor lattice, it can actually accept a magnetic field, and then the magnetic field lines get trapped in place and the magnet levitates. This is called flux pinning or quantum locking. This happens because perfect electrical resistance means perfect eddy currents, which generate a mirror magnetic field and locks the field lines in place. Flux pinning can even suspend the superconductor under the magnet. What's the difference between alternating current and direct current? Usually you'll see graphs of sine waves like this. I'd like to show you something a little more hands-on. Now you'll have to use your imagination. This is a DC source. So if this were a DC source and if these were electrons in the circuit, then since the source is direct current and never changes, the electric current always goes one direction back through the battery. If this were an alternating current source, what would happen is the current would go one direction, then stop, then it would turn around and go back through, and then it would stop and turn around over and over and over again, alternating back and forth. That's why it's called alternating current. In the United States, the current alternates back and forth 60 times per second. The reason the current is alternating is just due to the way it's generated. We turn generators which are rotating, and the rotational motion alternates the current. Ever wondered what the ozone layer is and why it's important? The ozone layer is a vital shield that protects life on Earth from harmful solar radiation. It is made up of a gas called ozone, which is composed of 3 oxygen atoms bonded together, and is located about 10 to 30 miles above the Earth's surface in the stratosphere. This layer plays a crucial role in absorbing 97% of the sun's dangerous ultraviolet rays, which can cause severe damage to living organisms. Ozone is destroyed by man-made chemicals, primarily chlorofluorocarbons. These substances were once widely used in refrigeration and air conditioning, and their use has now been limited. Without the ozone layer, the sun's intense UV radiation would make it impossible for most life forms to survive. It helps to maintain a stable climate and prevents skin cancer in humans, and it enables essential processes like photosynthesis. So this is the crystal lattice of ice. And you can see I have the same kind of molecules running around here as I do over here. I want to study this for a second. And notice what's going on. In the ice state, notice what's going on. Here you have this oxygen, and there's a hydrogen here, but the hydrogen is pretty close to the next oxygen over because it's attracted. This hydrogen is attracted to this oxygen. This hydrogen is attracted to this one. This hydrogen is attracted to this one, and so on. And so they're attracted because of what we talked about a minute ago, because it's polar. And when the thermal energy, when we cool it down and they stop moving so much, then they get locked into this position. But these atoms are farther apart, these molecules are farther apart than water can exist in the liquid state here, and so ice expands. This is a visual representation of why ice expands, because it gets locked into this lattice like this. This is the main punchline. All right, now you might look at this closely and say, well, wait a minute, he's got a couple of molecules here that don't look right. This one has a single oxygen, or hydrogen here, and one oxygen here. Where's the other hydrogen? Well, you see in this particular one right here, what you've got going on is one of them is going into the board. This one's drawn like this, where the hydrogen is coming down. There's another one going into the board that you can't see. And this one over here is attracted to another oxygen out of the plane of the board. And so this lattice for ice exists in 3-dimensional space, towards you, away from you, and across the board as well. Let's go ahead and put the chamber on and fire it up. Okay, water in a vacuum chamber. Here we go. 3, 2, 1, vacuum on. All right, 72.2. We're about 3/4 of an atmosphere. Notice the temperature is starting to drop almost immediately. We'll talk more about why that happens in just a second, but let's just take a look and see. We're at about a half of an atmosphere. 71.3, 71.1, temperature's coming down very, very repeatably. And notice it's starting to boil very vigorously. Actually starting to splash out of the container. 68, 67. We'll get a little bit lower in temperature, but this vacuum pump just can't do much more than this. So the real question is, why does the temperature of the water go down? We always think about boiling as something getting hotter and getting hotter and hotter, and so it boils. So why did we allow it to boil at a lower pressure without adding any heat? We already talked about that. That's just because we're removing the extra force on the outside, and that allows the water to escape off to the surface. That's what we call boiling. But why did the temperature go down? Well, when you think about it, inside of the liquid are molecules of water at different energies. Some of the molecules are traveling really, really fast. Those particular molecules have a higher energy. And some of the molecules are moving slower. And so some are fast and some are slow. And the ones that are traveling really, really fast eventually make their way to the surface, and they can escape and go straight up in to the vapor state, right? But the ones that are slower, they don't have quite enough energy to escape, even at the lower pressure. So what happens is, when we see the liquid boiling, what's really going on is the fraction of the water molecules that have enough energy to escape, the hotter ones in other words, those are the ones that fly away. So the ones that are left behind have to be colder. They have to be traveling slower, otherwise they would have already escaped. Learn anything at mathandscience.com.